So good afternoon, everybody. Thank you for coming down on this Friday afternoon. And it's a lovely, lovely weather outside, so it's nice to see you all down here in this dark room. It's my great pleasure to welcome Professor Vladimir Matolin to Kyushu University. Today I'm acting as chair, but I think really Brett, who's postdoc in I²CNER, should be acting as chair as a former member of his group in Charles University. Professor Matolin is a very esteemed professor in the area of catalysts and fuel cells in Europe, especially with platina and Syria systems, low temperature carbon monoxide oxidation, hydrogen oxidation reaction, especially in PEM fuel cells, and low platinum loadings. These are all key issues that we need to solve for these kind of energy problems that we're working with in I²CNER as well. And he's got over 330 papers in these fields. So without further ado, I'd like to welcome him to the stage, and if you could give him a round of applause as he comes on up. So thank you, everybody. Thank you.
Okay, Mr. Chairman, thank you very much for the introduction. First of all, I would like to say that it's a great pleasure to be able to come here to this beautiful place and to discuss this colleague, because we shortly visited some labs just a few minutes ago, and I found that there is a lot of things where we can probably collaborate in the future. So it's really very, very nice, and I'm very happy that I'm able to be here. Well, as the chairman said, so my name is Matolin. I'm from Charles University in Prague, and I'm going to talk about our research concerning quite unusual application of fuel cell technology, is the application of so-called thin film catalysts. First of all, very short introduction. So I'm coming from Charles University in Prague, which is the main university of the country in Central Europe, Faculty of Mathematics and Physics, and I'm head of the Department of Surface and Plasma Science, which is the department. We have around 100 PhD students, academicians, researchers and staff, and several laboratories, and the laboratory which is concerned with this talk, with these results, is Surface Physics Laboratory. In fact, the laboratory is composed of two unities, Surface Physics Laboratory and Material Science Beamline, because we have our beamline in cyclotron Elettra in Italy, which we have built there. And also this Material Science Beamline, Surface Physics Laboratory, is a part of Central European Research Infrastructure Consortium, which is a European consortium offering advanced infrastructures as open access to users coming from worldwide. Charles University is a very old university, one of the oldest in Europe. You can see that it was founded in the 14th century. Today we have 17 faculties and more than 75,000 employees, and a lot of accredited programs, doctoral programs, a lot of agreements with many foreign institutions, universities, and so on. And this is among of 2% of the best universities and 100 European universities. Okay, and now concerning my talk, so I will just show two different parts, but which are connected together. I will explain how we are preparing and what are the properties of thin film catalysts for a low platinum content proton exchange membrane fuel cell. I will present also some results concerning the fundamental studies, model studies of so-called single atom platinum serum oxide catalysts, and also I will talk about application of thin films for preparation of proton exchange membrane fuels and reversible fuel cells. The first part, or anyhow, the talk concerns something which you know very well here. Synergetic development of electric grid and hydrogen grid is probably one of solution for future in hydrogen cycle. So we need, if we are able to produce hydrogen from renewable energy coming from wind or solar energy, and after if we can convert hydrogen to electricity using the fuel cell, so we can store energy by using hydrogen. But of course, there's many other applications of hydrogen technology. One of the most popular is automotive application, is the use of fuel cell in cars. For hydrogen cycles, as I said, so we need two key elements. This is electrolyzer and fuel cell. In electrolyzer, we are splitting water to oxygen, to hydrogen, oxygen. In fuel cell, we are producing from hydrogen electricity. So in the first part of my talk, I will just show some results concerning the proton exchange member and fuel cells. Probably everybody know here how it is working. The key part of the fuel cell is the catalyst, which is supported typically by gas diffusion layer. Hydrogen splits to proton and electrons, and on the cathode side we are reducing oxygen and we are forming water. In the standard application, so we are using, or people are using powders, typically nanoparticles of carbon with nanoparticles of platinum. So this is the GDL, and GDL is coated with powder. So there are these two parts. And the problem, of course, of the fuel cell actually is the problem of cost, because the material which can be used actually really industrially is the platinum, which is very expensive. And for this reason, people are trying to find some alternative solutions, to find some cheaper solution. It means to replace catalyst by non-platinum by non-platinum or non-platinum group metals, or to use very low platinum loading. Okay, so in what I'm going to show here is preparation of thin film catalysts. This is, as I already said, is quite unusual, because typically catalysts are nanopowders prepared by chemical wet techniques, and thin film technology is generally considered as incompatible with preparation of large surface area, because the thin films typically are flat and non-porous. However, if we are able to prepare by using some special deposition parameter a high surface area, and if we are able to produce by thin film technology nanoporous catalyst film, we can profit all the possibilities of thin film technology. It means very fast deposition, easy deposition, environmental friendly deposition, and by combining the deposition technique, we can, or deposition system, so we can produce easily alloys, for example, by depositing simultaneously with different materials and so on. So what I will try here, I will try to persuade you that this technique can be useful in the field of fuel cell technology. We are using magnetron sputtering. This is standard deposition technique, which can be used as a non-reactive or for reactive deposition. In case of magnetron sputtering, we have a target, and we are creating plasma by radio frequency or direct high voltage, and the ions of plasma bombarded target and sputtered off the material from the target, and the material is deposited everywhere, so some substrate. And if the working gas is reactive, could be, for example, nitrogen, we can produce also compounds by reactive deposition. So this is the example of deposition of platinum and cerium oxide, because in our case we are combining the platinum with cerium oxide. Cerium oxide is amazing material because it's easily reducible oxide. We can switch very easily from cerium 3+ to cerium 4+. There is high mobility of oxygen, and it is used for so-called oxygen as an oxygen buffer. So the cerium oxide can take oxygen, oxygen can be easily removed back. It's used in many fields of catalysis, typically in automotive exhaust catalyst and so on. Well, okay, and now how we can achieve porosity. The example is here. So, for example, if we take atomically flat graphite foil, it means really very, very flat. And if we are coating this foil with different thicknesses of platinum or cerium oxide, you can see that we are creating very porous structure. It is not flat and it's not compact. And the porosity depends on deposition rate and also on the thickness. Thickness here means the deposition time. And if we check the cross view of the layer, we can see that in fact we are etching deep nanochannels inside the carbon substrate. So really we are etching the holes, which are coated with catalyst. The explanation is here. By deposition cerium oxide, we have oxygen which is removed from the target, but we can also add oxygen to the atmosphere, to the working gas, and create reactive plasma. And reactive plasma is etching carbon very easily. That means that we are removing partially carbon from the substrate by forming CO2. But at the same time, we are depositing cerium oxide, which is working as a nanomask, which means we are depositing nanoparticles, which are protecting cerium oxide below these masking particles. Which means that we are at the same time forming the particles and etching the holes. And this is what can be seen in this figure. Okay. This is the example how it works. Just as an example, we coated silicon wafer, which is also very flat, with thin film of carbon, which is amorphous. And you can see that after etching, after some time of etching, so we etch this kind of holes. On the other hand, if we use other type of carbon, for example, carbon which is doped with nitrogen, you can see that the etching is much more efficient, and instead of creating holes, we can go until some kind of nanonoodles which are coated with the catalyst. And if we are mixing the material between this and that, so this is something in between. So it shows that we are able to tune the porosity by changing not only the parameter of the deposition, but also by changing the material properties of the carbon substrate. Well, if we check how it looks like, in this case, you can see this is the hole. So this is TM image with EDS coated with a catalyst, and on the other case, you can see that it's etched down to the silicon substrate. And we have, again, so the platinum image, Syria, and it's a dark field image from the TM. Well, if we do that, the same process, but instead of using flat carbon substrate, we can use the carbon nanopowder. Carbon nanopowder, which is, we are coating GDL with nanopowder ink by spraying or by inkjet printing. And after, so we are preparing something like, we call that nano-GDL, so GDL coated with carbon nanoparticles. And after we coat that with Syria, or platinum of Syria, you can see that we have something like cauliflower structure. So again, we are etching the holes inside the particles. And because, as I have shown before, we can increase the efficiency of the etching process by adding nitrogen-doped carbon. So what we can do, we can also coat at first the carbon nanoparticle with this interlayer, and to etch and to deposit the catalyst after. You can see that the porosity is even higher, exactly as in the case of the flat model, which I have been shown before. So we can tune the porosity, and we have something which is really nicely porous. And so the process which we are using can be separated in different steps. The first one is GDL coating, nanomasking, selective substrate etching, porosity tuning, and ultra-thin catalyst film deposition. This process is patented. It's covered by 6 international patents. And if we check the performance in the fuel cell anode, prepared in this way by using only 4 microgram of platinum, which means that it's almost platinum free, because 4 microgram is so low loading that the cost is negligible. You can see that we can go up to 1.4 watt per square centimeter by using a state-of-the-art cathode, the commercial one, and just 50 micron thick naphthalene membrane. So it means that this anode, this 4 microgram, is meeting industrial requirements. We can also prepare thin film anode and cathode. In that case, the performance is not so high. We are at 0.5 watt, but the total loading of the MEA now is 50 microgram of platinum per square centimeter, which again is very low loading. Okay. Of course, the question is durability, because it's one of the main parameters, and so we can perform the heavy-duty endurance tests using fuel cell testing stations with possibility of cycling and programming the accelerated tests, and you can see that even after a 6,000 loop between open voltage and 1 ampere per square centimeter, we have almost constant performance of the catalyst. The catalyst is very stable, mainly if we use the platinum-doped carbon as a substrate. Well, now, in fact, the question is how it looks like, which kind of material we are using. If we check by XPS, by photoelectron spectroscopy, we can see that the platinum is not metallic. Platinum, after deposition, is ionic in the platinum 4+ at platinum 2+ state. There is no metallic platinum. And explanation, it's here. So in this Angemantra Chemia paper, which we published a few years ago, this is the cover page, and just by comparing the experiments and doing the DFT calculation, we propose that the high stability and activity of catalysis is due to the anchoring of single platinum ions between square nanofacets, square oxygen of 100 nanofacets on Syria nanoparticles. Because even if we are using thin deposition, it's polycrystalline. We are forming a layer which is composed of an average 5 nanometer nanoparticles with different surface planes. And the stability of this atomically separated atoms is higher than stability of metallic platinum, and the catalyst is, the platinum is not sintering. This is something which is called, now is quite popular, as a single atom catalyst. Okay, and now of course what we wanted to see if we really have the single atoms, which is not so easy, because the contrast between Syria and platinum is not very high. So what we tried, just we profited situation that then in maybe 2 months, 3 months ago, one of the most worldwide most performant TM was installed in the Material Science Centre in Trinity College Dublin, and just we came there and we tried to look for this single atoms. This is what we call the platinum galope, because they are the single atom of platinum which are moving because they are excited by the electron beam. Unfortunately, we cannot obtain the stable image because the energy was 200 kiloelectronvolt. And the platinum just make a hopped in between this specific position where the platinum ions are stable. But at least this is some proof of atomically dispersed platinum. Well, so this is the summary of the first part. So thin film technology opens new way in catalyst preparation, and by combining metal with oxide, we can prepare new classes of materials. Now, of course, it would be very interesting to see how it's working and why we can obtain this very nice activity. In our group, we are focusing a big effort to so-called modal studies. The modal studies in catalysis means that instead of preparing the particles, nanoparticles, which has a lot of corners, kinks, and different planes at the surface, we can prepare atomically or, atomically controlled flat surfaces where we can create well-defined structures of oxygen vacancies on steps and so on. And by checking the reactivity of these models, where we can modelize also the morphology of the surface, we can investigate, for example, which plane is more reactive than other one, and so on. Well, in the case of silicon oxide, so we need to control two things, is the stoichiometry and morphology. Stoichiometry means to prepare the Syria, which is partially or fully reduced. For that, we proposed quite a new technique, is a reduction of cerium oxide by cerium. Because cerium metal is very reactive, so we are preparing at the first cerium O2 111 buffer layer, and after by depositing Syria, so we are reducing surface and increasing concentration of cerium suprastates. You can see the example here. For example, this is C2O3, which is fully reduced to the second stable structure, which is in this case the cubic structure. We are controlling stoichiometry by XPS, but also by resonance spectroscopy at synchrotron. I will explain later how it works. We can see by electron diffraction the different reconstruction corresponding to different degree of reduction, but still single crystalline. And also we can check, or we can perform DFT calculation by comparing the results of theory and experiments. The other important steps is to control the morphology. Morphology means that control the density of single atomic steps at the surface by scanning tunneling microscopy. So this is the image of CO2 111 on copper 111 substrate. And you can see that by changing the properties or by changing the deposition parameters, annealing and so on, we can change the density of steps in a relatively large region. So it means that we can control the morphology and we can control the stoichiometry. And now, if we can use this kind of model for investigation of platinum interaction with cerium oxide. Here you can see, this is a very new paper published this year, showing that where we prepared the different type of surfaces. So this one is cerium O2-111 with very low density of surface oxygen vacancies, and we deposited, in this case, 0.06 monolayer of platinum. And you can see that the platinum is in two states, platinum 2+ and platinum 0. Okay, previously I showed that we have also platinum 4+, but I forgot to say that platinum 4+ is not stable. It's some kind of defect where the platinum is in the lattice of ceria, and after annealing or reduction in hydrogen, as the platinum 4+ is reduced. Well, so if it's flat, we have, after depositing this amount of platinum 2+ and 0. If we have the same surface but partially reduced, is also very low concentration of steps, we are again forming the platinum particles. This is also platinum particles. And in that case, we have only platinum 0, which means that if the surface is reduced, there is no formation of platinum 2+, which is not very surprising, in fact. Well, and the third example here shows stoichiometric cerium oxide with very high density of steps, and you can see that by depositing the same amount of platinum is completely oxidized, so we have only platinum 2+. And if we check these islands, we can see that we have monolayer high islands of ceria, but we don't see any platinum particles because the platinum is atomically dispersed around. Well, and now returning back to the first case of stoichiometric surface with low step density. You can see that in that case, so we deposited two different amounts of platinum at the surface. For 006, you can see that, we change the density of steps. This is the low, this is the highest, and now we perform the experiment by changing density of steps. And you can see that for low density, platinum 2+ concentration is here. But by increasing the step of density, we are increasing the concentration, but after we have a plateau. Because we have all platinum is fixed at the steps in form of Pt2+. If we deposit the higher amount of platinum, we have the increase of platinum 2+ concentration, because more steps means more sites for platinum deposition or platinum anchoring on the specific sites. Well, the model is here. We can check different type of platinum at the surface, the platinum of oxygen vacancies, by calculating binding energy of platinum is 2.8 eV. If the platinum is on the terrace, it's here. It's on the flat surface, the binding energy is here. Platinum in nanoparticles, binding energy, and the platinums at the stoichiometric steps. The binding energy is 5.0 eV, which means that again we have a square for oxygen, exactly as in the case of the small nanoparticles of platinum. So this model, flat, and the particles are going well together. Other things is we can check how it depends on the stoichiometry of silicon oxide. As I said, we are using resonance spectroscopy, which is maybe 100 times more sensitive techniques than the standard XPS. This is a so-called 4F4D resonance. There is no time to explain. However, if we are tuning the energy of light at the synchrotron and measuring the concentration of cerium 3+, we are going to the maximum in the valence band, and at 2 eV and at 4 eV we have other maximum for cerium 4+. Well, so we are able to check it very well. And again, if we are changing the density of steps, we are checking the cerium 3+ concentration. This image, this picture shows that in the normal situation, the platinum is reducing cerium oxide due to the charge transfer. The charge transfer, there is the paper also from this year, which we have published, showing which is the charge transfer between platinum and cerium oxide. And we can show that there is in fact no reduction, practically no reduction of ceria, which is surprising, more or less. Now, and again, it can be explained that we have two types of steps, stoichiometric steps and oxidized steps. If we add one oxygen at the steps, we have 5 oxygen around, and very simply or rapidly showing that we have binding energy 6.6. So again, even more stable platinum. And it shows that again the platinum 2+ is located in platinum of 4 units and 1 or all steps with excess oxygen. Well, this is probably too fast, but the message is that the platinum is really atomically dispersed. So the summary of the second part, the platinum of 4 units are carrying monodispersed platinum 2+ ions, which can be considered as elementary building blocks of single atom platinum ceria catalyst. So this is what we are calling the single atom catalysis by platinum. The problem is, of course, that we don't know really very well what is the role of ceria here. We don't know that yet. If it's only stabilization of platinum, or if cerium oxide is activating hydrogen bonds. So it means the splitting hydrogen 2 molecules into hydrogen atoms. And now I will go rapidly to this last part of my talk, and it concerns this. So I will again returning back to the real catalysts, but still thin films, and will explain or will show you how we can prepare thin film catalyst, which is active for proton exchange membrane water electrolyzer. So again, you know that very well. So typically water splits on iridium catalysts. Okay, if you check in the literature, the performance of electrolyzers, you can see that the voltage and corresponding current, you can see that of course the better catalyst means that we have at the same voltage lower current. It gives higher efficiency. So it means that actually what is published somewhere in between these two borderlines, and the typical anode loading where iridium is used is 1 to 2 milligram of iridium per square centimeter. We are using again certain deposition. We are depositing iridium at the surface, but of course we cannot use here carbon nanoparticles because it's because of highly oxidative potential, and we are replacing carbon nanoparticles by titanium carbide, which is very well conductive, as much more stable at the at the high oxidative potential. Of course, also the GDL should be replaced by something more stable. In that case, the results I will show here were obtained by depositing titanium carbide on titanium mesh. And you can see that by coating the substrate with 80 microgram of iridium per square centimeter, which is again much lower value than in case of state-of-the-art catalyst, we are somewhere in between these two borders. This is our performance we have. Well, the problem of this hydrogen cycle is that we need two key parts. We need fuel cell and electrolyzer. Of course, much more sexy solution would be to have something which can replace both. And this is also a reason why people are trying to find reversible fuel cells which can work in both sides. So we are also focusing our effort in this direction. So here you can see the results I have shown before. Iridium, pure iridium thin films is giving this performance. And so this activity. And by adding iridium, you can see that we have almost the same results. We added iridium not in form of alloy. This is what people are trying to do, but alloy is not very, very active. We make a special procedure by separating multi-layer or double layer of platinum and iridium by electron and ion conductive barrier. Which means that by adding platinum, it's not better, but it's not worse. Yeah, it's quite pure iridium. Okay, now if we check this platinum iridium double layer as a proton exchanger, as a fuel cell, as a potential fuel cell, you can see that quality of the results of performance of the cell is the same with and without iridium. So it's very similar again. Iridium doesn't help, but it's not worse with iridium. Which means that we can use this platinum iridium multilayer as an anode of electrolyzer and also as an anode of the fuel cell. And again, with relatively very low loading, because we check that also with thin film platinum as a cathode. So we have loading which is maybe 50 times lower. Okay, and the last just things that we are trying to commercialize. So there's a technology transfer. So we founded a startup company, Linked Fuel Cell Technology, and we are trying to persuade industrials that this solution can work. This is our booth at the Hanover. This is the picture of our fuel cell testing laboratory we have in Prague with our fuel cell testing stations. We have 10 actually, because for durability is very important. And actually we are just sending samples to Ballard and other companies for just checking the performance. Well, okay. And the summary, I hope that at least partially I persuaded you that thin film technology can be useful, even is very unusual in case of catalysis. I think that we are pioneering more or less this technique. So magneton sputtering can provide efficient nanoporous layer, and we can meet industrial requirements with this type of catalyst. The funding, so there are several projects. This one is quite important. This European chip cut project, design of thin film nano-catalysts for on-chip fuel cell technology. We have 8 partners, including companies like Solvicor companies now is Greenity company, because Solvicor was purchased by Toray, actually like a Japanese, no more German. And we have the different grants coming from different sources, European, Czech consortiums, and also we are supported by investor, because the Linket is supported by Jablotron Group company, and of course also by Charles University. Okay, thank you very much for your attention.